So we're looking here at the model of a parabola where we have y equals ax squared plus bx plus c, and we've set b and c to 0 and a to 1. So we simply have the basic form y equals x squared, and we're going to play around with a, b and c to see what happens to the graph when we do that. So first of all, if we look at a, the coefficient of the x squared term, we currently have a is 1, which gives us a positive upward parabola with a minimum. And if we adjust a further upward, we can see that the result of that is that we get a steeper, sharper parabola. So on both sides it rises more sharply to infinity, the higher the value of a. And if we come back down, we can see that it gets wider and flatter as a gets smaller, hitting a equals 1, and then going below that it gets much wider and flatter until we reach a equals 0, which yields effectively y equals 0, which gives us that flat line. Then if a is negative, we have the same thing reflected in the in the x-axis, about y is equal to 0. So a equals minus 1, and then if a becomes greatly negative, then we have a sharper descent towards negative infinity. And so we'll place that back at a equals 1, and we'll now look at b and c. Having a look at b, if we take positive values of b going upward to 1, we can see the parabola now moves to the left and downward. So it's intersecting the x-axis at 0 and 1 now. Y equals x squared plus x, which factors into x plus 1, which if we set equal to 0 gives us either 0 or minus 1, which makes sense according to what we see here. And as we adjust that even further, we'll take that down to 5, that becomes y equals x squared plus 5x, which factors into x plus 5. If we set that to 0, we have x is equal to 0 or negative 5, which are the 2 points where it cuts the x-axis. So that makes sense. That's consistent with what we see. Now if we shift b, if we adjust b to becoming negative, the parabola now moves to the right across the y-axis and descends on the right-hand side. So that's the effect of the b coefficient. And if we look at c, this is the simplest of all. C simply lowers or raises the graph. So if c is positive, it raises the graph by that much. And if c is negative, it lowers the graph by that much. So the most interesting one probably is b in terms of how it shifts the graph. This is a problem I came across recently. It's to determine the coefficients for a parabola given constraints that are placed on it. Okay, so to recap, the most general form of a parabola takes y is equal to ax squared plus bx plus c, where a, b, and c are elements of r, though they're typically integers, and a is not 0. If a was 0, this would simply reduce to being a line, that is y equals bx plus c, which would intersect with the y-axis at c. But we are specifically looking at parabolas, so we set a not 0. The first condition we have is that for x equals 1, y equals 0. The second condition we have is that for x equals 0, y is equal to 10. The third condition we have, which nails us down, and which is an interesting one, is that we have a maximum value of 18 for the parabola. Now, getting back to the first condition, what this tells us, if x equals 1 and y equals 0, then the equation of ax squared plus bx plus c reduces to a plus b plus c being equal to 0. Going back to the second condition, when x equals 0, y equals 10, this reduces to, when we substitute x equals 0 into the equation, y is equal to c, which is equal to 10. So straight away we have a value for c. Now looking at the third condition, a maximum value of 18. Typically when we see a parabola, it has a minimum value. That is, it goes upward on both sides from a minimum point. But if the coefficient of the x squared term, that is a, is negative, then it will be inverted. So it will have a maximum value rather than a minimum value, and it will go downwards as x gets greater, and also as x gets progressively more negative. So that tells us that if we take the derivative of fx, we look at f dash x, and we set f dash x equal to 0, that will give us our critical point, or the point at which the maximum occurs. And if we substitute that x value back into the original equation of fx, that will give us 18, which is the maximum value in this case. Just a recap on derivatives. When we're looking at powers of a variable, the derivative of a times x to the n, where x is our variable here, is n times a times x to the n minus 1. So in the case of our parabola, fx equals ax squared plus bx plus c, f dash x, or the derivative, is 2ax plus b. So just to recap also on critical points, when we set the derivative equal to 0, whatever values we get back indicate where the critical points of a function are. But for a parabola, it's only 1, which is the minimum or the maximum point. But for instance, if we're dealing with a cubic, we might have 3 points, a maximum point, a minimum point, and a point of inflection between them. But in this case, we're looking for our maximum point. Now going back to the original equation and looking at the conditions, for x equals 0, y is equal to 10, recall that yielded y is equal to c, which equals 10. Now if c was 0, we would have a maximum point of only 8, but because we've got c is equal to 10, this has shifted the graph 10 units upwards, so the maximum point is 18, where it otherwise would have been 8 if c had been 0. So that revealed to us that we can write our equation as fx is equal to ax squared plus bx plus 10. Now looking at the second condition, we had when x equals 1, y equals 0, which gave us y is equal to a plus b plus 10 is equal to 0. And that can be expressed as a plus b is equal to minus 10, which will come in useful later. Now recalling the third condition, a maximum value of 18, let's set the derivative equal to 0. The derivative is 2ax plus b. Set that equal to 0 and then we solve for that. So this produces a value of x is equal to minus b on 2a. Now we go back to the original equation of fx equals ax squared plus bx plus c, and we substitute in that value of minus b on 2a, and also we substitute 10 for c. So we end up with a times minus b on 2a squared plus b times minus b on 2a plus 10 is equal to 18, and then we proceed to solve this. The first step I make here is that I simplify the numbers so that they're all on one side. So instead of plus 10 equals 18, we will subtract 10 from both sides, and we have the algebraic expression on the left is equal to 8 on the right hand side. Now multiplying through into the brackets, in both cases we get a times b squared over 4a squared minus b squared on 2a is equal to 8. And the next step is to find a common denominator for these two expressions on the left. That common denominator becomes 4a squared, which is the denominator for the first term. The second term is 2a. That factors into 4a squared 2a times. So we multiply the numerator of the second term by 2a. And what we end up with is ab squared minus 2ab squared all over 4a squared. And we will now simplify that. And so that gives us minus b squared over 4a is equal to 8. And multiplying through by 4a, and recall we can do this because a is not equal to 0, we get 32a plus b squared is equal to 0. Okay, so I've written in matrix form here the information that we have already. So from the first condition, we had a plus b is equal to minus 10. Now, if we look at what I've written, I've constructed three matrices. First of all, a 2 by 3 matrix with the 1s and 0s, then a 3 by 1 matrix, or 3 by 1 vector with the a, b, and c, and then on the right-hand side, a 2 by 1 matrix with minus 10 and 10. That represents the equations that we saw earlier and that we can see on the right-hand side. So looking at that left-hand matrix, the 2 by 3, we have 1, 1, 0, which multiplies into the column vector ABC and gives 1 times A plus 1 times B plus 0 times C, or A plus B. And that is equal to the top entry in the right-hand 2 by 1 matrix, 10. A plus B equals minus 10. Now, if we look at the bottom line in the left-hand 2 by 3 matrix, we have 0, 0, 1. That multiplies into the column vector ABC to give 0 times A plus 0 times B plus 1 times C, or just C, which is equal to, on the right-hand side, the lower entry of that 2 by 1 matrix, 10, which, as you can see on the right-hand side, in blue, I've put C equals 10. Now, I've just put up the material underneath that from slide 14 earlier, which is where we saw y equals c equals 10 and y equals a plus b plus 10, which is equal to 0. And all I've done above is just to represent that in matrix form. So now I've just joined this to create the augmented matrix, which is basically the coefficient matrix above the 2 by 3 matrix, and that line, that vertical line, indicates separation between the coefficient matrix and the matrix of solutions or values, so minus 10 and 10. The other piece of information that I use at this point is the equation that I derived earlier by looking at the derivative, which was 32a plus b squared is equal to 0. And together with the augmented matrix, we'll be able to now find values for a and b. So the next thing to see is that if I substitute for a or for b into the right-hand side equation there, 32a plus b squared, I will end up with a quadratic in terms of either b or a. And then when I factor that, I will get my values of either b or a. And once I have the b value, I can find the a value. Or once I have the a value, I can find the b value. So now looking at that equation on the left-hand side, a plus b equals minus 10, we can rearrange this either in terms of b or in terms of a. So first of all, I'll do it in terms of b. And that gives me b is equal to minus 10 minus a. Now I can substitute this into my 32a plus b squared. So here's my equation, 32a plus b squared, and down below I'll make this substitution. So my first line becomes 32a plus bracket minus 10 minus a bracket squared, because that's what b is from above. And now we will expand that progressively and solve it. So the next step, when I multiply out that square bracket, is 32a plus 100 plus 20a plus a squared is equal to 0. When I collect the terms now, I end up with a squared plus 52a plus 100 is equal to 0. And then I can factor this into a plus 2 times a plus 50. And I can reconstitute that, if I want to go backwards to the line above, by the following. There's an acronym, FOIL, FOIL, for quadratics. So FOIL stands for F, first, so the first two terms, a times a, O for outer, the outer two terms, a and 50, I, the inner two terms, 2 and A, and L, the last two terms, 2 and 50. So each of those we take the product. So FOIL, the first two terms, A and A, is A squared, which we see above. And then O, the outer two terms, is 50 times A. I, the inner two terms, is 2A. 50A plus 2A is 52A, which is the middle term above. And L, the last two, 2 times 50 is 100. So we get A squared plus 52A plus 100, a useful acronym when dealing with quadratics. So in solving this, if we have a product which is equal to 0, that means one of those terms must be 0. If it's the first term, that yields A is equal to minus 2. And if it's the second term, which is 0, that would yield A is equal to minus 50. And given that we have the expression at the top of the page, the top right, for B, we simply find B for the corresponding A value by plugging A into that equation. Now, just for interest, I've changed that equation on the top right to red, and I've written it in terms of A. So if we substituted for A, we would have A is equal to minus 10 minus B, and we're now going to plug that into 32A plus B squared equals 0 to see what values we yield for B, for the quadratic in terms of B. So at the first step, we have 32 times bracket minus 10 minus B bracket plus B squared equals 0. So multiplying through, we have minus 320 minus 32B plus B squared equals 0. So now we get B squared minus 32B minus 320 is equal to 0. The next step is to factorize. So we're looking for two factors of 320, which have a difference of 32, and that gives us B plus 8 and B minus 40. So if we have B plus 8 times B minus 40 is 0, as before, either the first factor is 0 or the second factor is 0. If the first is 0, we have B equals minus 8. If the second is 0, we have B equals 40. So B equals minus 8, B equals 40. So we have now A equals minus 2 on the left, which corresponds with B is equal to minus 8. And then we have A equals minus 50 on the left, which corresponds with, on the right, B is equal to 40. So let's construct our quadratics. And there is our first one. Y is equal to minus 2x squared minus 8x plus 10. And there is our second one. Y is equal to minus 50x squared plus 40x plus 10. Now the next thing we will be doing is looking at these on a graphing calculator to see exactly how, visually, they meet the conditions that were set down originally. So we're looking now at both of these graphs. On the left-hand side, you can see y equals minus 2x squared minus 8x plus 10, and below that, y equals minus 50x squared plus 40x plus 10. The upper equation refers to the blue parabola and the lower equation to the green parabola. And looking at these, we can see that they both have a maximum value of 18. So the third condition is met. And as far as the first condition, when x equals 1, y equals 0, we can see that at the value x equals 1, both of these parabolas cut the x-axis, having a value of y equals 0. And for the second condition, when x equals 0, y equals 10, we can see they both cut the y-axis at 10, meeting the conditions set down. So either one of these is solution to the three conditions that we laid out initially. All right, thank you for watching. I hope that was useful in giving some explanation of how we can manipulate things in order to solve rather sophisticated equations, in particular this parabola problem. I'll be uploading more videos as often as I can, typically in the field of pure maths, maybe around algebra, calculus, and other types of problems related to that. So if you enjoyed this, please feel free to subscribe and follow me at Michael Angland Maths. Thank you very much.